this computer. And we are going to go ahead and get started. Um, we are on day 2 of enzymes and did some adjustments to my PowerPoint so that I can kind of do a better job of keeping us on track and keeping myself on track so I don't like ramble or go bonkers and sideways or anything because that really doesn't help anyone. Um, Now, with that said, oh, I see there's a note about group me. Um, I don't know if anyone did, but go for it. Great tool for communicating. Okay, so enzymes again, and don't worry, I'll mix it up on day 3 and 4 of enzymes. Um, what I'm trying to do, and my approach to introducing enzymes and my rationale here is to get you to understand kind of the concepts and then as the days go on, we'll get a little bit further into some of the details. So if I could draw an analogy, it's almost like right now we're going through the process of learning how to play chess, and I'm telling you, hey, well, um, one character can move in this direction, another character can move in this direction, but I have yet to identify that this is a pawn, this is a rook, this is a bishop, this is the king, this is the queen, and so on. We're going to get to that a little bit more next week. So, with that in mind, we're kind of going to look at learning objectives from last time. And last time, what we did, we tackled the generic enzyme, that Cleland notation, um, the ES complex, the EP and EP complex. I want you to be able to draw or identify free energy diagrams for a reaction in the presence and absence of an enzyme. And to give a quick snapshot of that, that was okay, where's my screen? There it is. It's not what I wanted to do right now, though. That would be, here's 2. Our y-axis is free energy. And then our x-axis is, I guess, reaction. So it went like this. And then with an enzyme present, we went a little bit like this. So it just went a little bit under. Number 3, be able to recognize the 3 main classes of multiple substrate enzymes. Multiple substrate enzyme reactions. These were our I believe that I referred to them as bi-substrate reactions, in which case that would be our ping pong mechanism, the random, and the sequential mechanism. I don't know why the word random escaped me. Now, for today, what we're going to look at, it's a little bit more, but as kind of a general overview, we're going to look at a couple of different graphs. We're going to go deeper into the Michaelis-Menten graph and look at the Michaelis-Menten equation. Then we are also going to look at a Lineweaver-Burke plot. And last but not least, we're going to talk about enzyme inhibition. So, a reaction stopping for whatever reason, or being stopped for whatever reason. Now, detailed look at that is we're going to reproduce the Michaelis-Menten equation, use it to describe the relationship between substrate concentration and velocity. We're going to know the difference between reversible and irreversible inhibition. We're going to be able to recognize and draw the Lineweaver-Burke plots you'd expect from an inhibitor that affects both Vmax, Km, or both, which if those terms all sound completely distant to you, we're getting there. Calculate Vmax from a velocity and a substrate concentration, or a Lineweaver-Burke plot. Then understand the 2 assumptions that we have to make in analyzing enzyme kinetics using Michaelis-Menten, and know and be able to describe the 4 types of non-covalent enzyme inhibitors and the effect of different types of inhibitors on the apparent Km and Vmax. Now, that last one, if there's something that I'm like, this is absolutely important, it would be that. I want to talk about enzyme inhibition because it's a couple of different graphs and conceptually it's tough to wrap your mind around. I've got some models that we'll look at for this, but it's still like it's tough. And so I want you guys to have more time with it. So we're going to introduce enzyme inhibition today. We're going to revisit it on Tuesday and not on Tuesday, on Monday, and then again on Wednesday. And we'll do it again before the exam. So I just want to make sure that we have a good chunk of time with enzyme inhibition. Now, to kind of review and reflect, we talked about these models. Our Cleveland notation with E plus S yields ES. ES asterisk indicates that our reaction's taking place. EP means that our product is bound to our enzyme. And then last but not least, we have our free enzyme. Now, with that in mind, we have our free enzyme and our free product that is released so the process can begin all over again. Here's a couple of different models that we looked at with respect to bisubstrate reactions or our multi-substrate reactions. We had the ordered mechanism, which is this is our ordered sequential mechanism right here, where there is an exact sequence that has to take place. What that means is that I'm going to go ahead and write EB, and I'm going to put this in a circle, and I'm going to say no. And what I mean by that is this specific enzyme has to bind one substrate before it binds another or a different one. A and B are simply variables and placeholders there, so don't get stressed about that, but just know that there is a sequence, there is a pattern, and there are some enzymes that observe or exhibit this ordered mechanism where they have to bind one before the other. The alternative to that, or in contrast of that, is, well, an enzyme doesn't really care which one it binds first. In which case, we've got our random reaction where, well, it could go down this pathway or could go down this route, where it will bind substrate A first, and then it will bind substrate B, or it will bind B, and then it will bind A, or A, then B, and so on. And then the same thing goes for product release and the sequence in which those products are released. Last but not least, which is kind of our most fun, but I think it's kind of tough to wrap your mind around, is our ping pong or our ternary mechanism. And I want to give you guys another kind of model of what that looks like. But before I reveal the next page, oh, yeah, that's what I can do. I can pause my share. Okay, and here we go. And nope, that's not what I wanted to do. I instead wanted to do that and done so. Okay, now clear that. Okay, so resume the share. Here what we have is aspartate. Just as a little bit of to jog your memory, is that one of our proteinogenic amino acids? And what is the single letter code for that proteinogenic amino acid? Single letter code for aspartate, also known as aspartic acid, is D. Now, in this case, we are looking at an enzyme, E down here, that will bind aspartate. Okay. And whenever it binds aspartate, what it's going to do is it's going to take this group right here and transfer it from itself onto, or sorry, transfer it from aspartate onto our enzyme, which is where, now I have to reveal my drawings there, which is where we get this right here, this ENH3. So this NH3 from aspartate has been transferred to our enzyme. This ENH3, if you remember, the kind of unique characteristic about the ping pong mechanism is it has a different form of our enzyme. So something about our enzyme, E right here, has to change. Does everyone follow that part? And in that process, that transfer of that NH3 onto our enzyme is going to release the first product. That first product is alpha ketoglutarate. Now, the details of the molecules that are released, I don't want you to stress about that and think about that, but that's kind of what's progressing here. So our first, sorry, let me erase. Our first product, so this would be substrate 1, aspartate. Oxaloacetate is aspartate, but without that NH3. So I'm going to label this as OAA, and that is aspartate minus NH3. Okay, so that is oxaloacetate will be released. Then what's going to happen is our modified form of our enzyme, this ENH3, that is going to bind alpha ketoglutarate. What would we refer to alpha ketoglutarate if we were to look at this right here, looking at this mechanism, this model at the bottom? Which one of these letters is alpha ketoglutarate? Add to the chat as soon as you see it. And just to give you a little bit of a memory jog, A is our aspartate. That has come in. Absolutely right. B, this is, now I'm going to jump ahead. This right here is B, our second substrate. So our second substrate, alpha ketoglutarate, binds to our substrate, or binds to our enzyme. What do you think our enzyme is going to do now if you ignore all of this? Our modified form of our enzyme, ENH3, what do we have to do to get back to E? We've got to transfer that NH3 onto, so this right here goes onto alpha ketoglutarate. And in the process, we make a different amino acid, glutamate. Now, all of this that's taking place is what's known as a transamination reaction. Now, I think that it's helpful and supportive to know some of these details. In a nutshell, what's happening is our enzyme is transferring NH3 from aspartate onto, and I'm just going to label it shorthand, and this is the cool kids do this, onto AKG, alpha ketoglutarate. And the result there is, well, we get glutamate and oxaloacetate. Now, with that in mind, when you look at this and you do something kind of broadly and you treat it the way that a chemist treats a chemical reaction, you say, not interested in that, not interested in that. What I'm caring about and what I care about is basically my inputs and my outputs. Now, have I grossly underestimated what chemists care about whenever I say all that? Yep, I have. I apologize for that. I don't mean any disrespect or anything like that. But this gives a little bit of an illustration as to what kind of the biochemist cares about in terms of where different groups are going and how they're getting there. NH3 goes from aspartate onto alpha ketoglutarate. Great. Alpha ketoglutarate, whenever it takes on that NH3, what is alpha ketoglutarate whenever it's aminated? What does it become? Add to the chat. Perfect. Glutamate. Wonderful. Great job. That's awesome. Okay. So this is just a little bit of a review. refresher on some of the high points of what we discussed last time. Now, what we are going to do is go back to where we kind of left off. I showed you this graph right here. This graph shows all of the different species and all of the different players that are involved in understanding how an enzyme basically behaves, how it functions, and what you get from an enzyme catalyzed reaction. The players that we have to care about and that we are interested in are the substrate. We are also interested in the product that we're actually generating, the enzyme, and the enzyme substrate complex. Now, there are some kinetic considerations with respect to this. I think this is a good graph to kind of look at. All right, well, our y-axis is just measuring concentration of all of these different things. What happens to the substrate? Well, as soon as the substrate starts getting used, the concentration drops off pretty dramatically. Well, the product goes up kind of inversely to the substrate's drop. The enzyme, the free enzyme, and that's an important thing to distinguish, free enzyme versus the enzyme substrate complex. Our free enzyme concentration drops down, and then over time, it increases. A fair question there would be, well, why does the free enzymes concentration here, why does that increase? Well, one reason is what is the enzyme? What does the free enzyme kind of go to? Our free enzyme goes to the enzyme substrate complex, ES. So the concentration of ES is dependent on the concentration of our free enzyme or the availability of our free enzyme, but it's also dependent on what other variable or what other component. Add it to the chat. S, our substrate's concentration. And where I've got those circles, our substrate concentration is almost completely depleted. So it kind of makes sense that our free enzyme has gone back up because the amount of that enzyme substrate complex has gone down considerably. Now, whenever we're studying an enzyme, what we're interested in is what's known as the steady state. So the steady state is where there's a couple of things that we can assume when it comes to Michaelis-Menten kinetics. One of those things that we can assume, I'm going to toggle forward here, is that we can assume that our concentration of our enzyme substrate, so this right here, this block here, is that steady state range. Our enzyme substrate concentration, that complex's concentration effectively hasn't changed very much. And the reason is, the reason for that is because our enzyme's concentration, the enzyme substrate complex is being produced and it's being utilized at a pretty even rate. So what that means is that, yeah, we're using up the ES complex to make our product, but also we're making that ES complex come to be. So we can assume this is at an equilibrium of sorts. So the consumption of ES is, let me think how to best word this. So the consumption of the ES complex, what I mean by that is ES going to E plus P. That ES complex's concentration doesn't deplete when we're talking about the steady state because the E plus S and the production of the ES complex basically cancels this out. So just as much as the product is being generated, and therefore the ES complex concentration is being depleted, the ES complex is being reproduced because our free enzyme and our substrate are coming together to make that ES complex again. So that is one of our big assumptions. Another big assumption is that we can assume that our enzyme is saturated with our substrate. Whenever we're studying Michaelis-Menten kinetics, we're imagining that every place that the substrate can go on the enzyme, it's going to. Now, just a little bit of a refresher and add to the chat anyone who feels comfortable with this. And if you want to send me a direct message, by all means. Um, what is the substrate? Just so we don't get, I don't lose anyone when talking about that. Or what is a substrate? It's a reactant. Our enzyme being our other big, that's great. The thing the enzyme binds to, absolutely. Our enzyme's going to bind to our substrate and either break a bond or it's going to bind to another substrate and fuse those two together to make a bond. Okay. So when we talk about Michaelis-Menten kinetics, one of the things that we're super interested in is basically how fast can an enzyme catalyzed reaction go? We want to know what is what's the top speed of it? That's one variable that we want to know. And to get the best answer for that, what we do is we basically saturate the enzyme with the substrate. So when we're doing enzyme studies, what we're looking at is kind of a progression from a low substrate to a high substrate. These, what does that look like to, I don't know, like a, a Pac-Man who's maybe a geriatric Pac-Man, we'll say. I'm thinking of my grandparents who had false teeth. Um, this is it's a Pac-Man, and this is our substrate, and we got a low substrate concentration, mid-level, and then a high substrate concentration. Initially, that low substrate concentration, not all your enzymes bound to it, but then at the very end, we've got so much substrate that every single enzyme has that substrate bound and can process it and go on and bind the next one. So when you do an enzyme study, think about it as you start out with low concentrations and then you work your way up gradually. Now, if we look at this right here, this graph, this is known as a Michaelis-Menten plot or an MM plot. Our y-axis is our initial velocity or our rate. Our x-axis is our substrate concentration. Now, one of the things that I was talking about the other day, I gave that hypothetical enzyme, the Oreo cookie lyase, where we had a product and we kind of monitored the production. The monitoring of our production is basically our rate. And if you remember, we had a bunch of different trials. We'll go T1, T2, T3, T4, T5. And we have a couple of different things that we want to keep into account. I mentioned last time that our enzyme concentration is going to be fixed. It's not going to change at all. What will change across these different trials is, first of all, our substrate concentration. And it's pretty reasonable to start out with something like 0. Say, how much product? This would be a good negative blank, or a negative control, sorry. How much of your product is going to be generated if you give it no substrate? The answer should be 0. Then we'll go to 1, 2, 4, and then we'll go to 8. And you do so many of these trials, you do them so many times that you ultimately are going to be able to cook up some error bars. Now, does anyone think that they have an idea of what your substrate concentration units would be? Typically, we'll go with typically. Moles. We're going to do moles, but we got to have a concentration. So something like molar. Molar would be pretty high, would be crazy high. So let's go ahead and say something like NM, nanomolar. Small amount. NM, NM. So nanomoles per liter, nanomolar. Now, our velocity. Okay, well, you know, You can think of yourself sprinting, driving a car, whatever. You've got a rate of change where it's like I travel this distance in this amount of time. Meters per second would work. For this, what we want to do, typically when it comes to velocity, we're thinking about the production of our product or the generation of our product. So our product is going to be some compound. And, I think it's pretty reasonable to say something, a velocity would be something like, let's go again with nanomolar, and let's just go with per minute. So there you're tracking or you're monitoring the concentration of a substance, and you've got a time interval. This is how much nanomolar of, and I like to go ahead and add in product per minute. Okay. And, let's go ahead and throw some numbers in there. 0, let's go with 2, 4, 5, 5. Okay, so we did 5 trials, and I just threw some kind of silly numbers in there. Um, Based on the trend that you're seeing here. And just so we're all on the same page, I'm not a mathematician. And I just kind of put some numbers in. Um, I'm going to say that my numbers kind of look like this. My first 5 trials. I've got my very first one down here in my origin. Then I'm going to say trial number 2 right here. Then, okay, well, my velocity goes up to 2. Then my velocity is going to double going up to 4. So this would be T3. Then what happens to my velocity as I increase? I've doubled my concentration on my substrate. I erase this and instead, so here's 1. I'm looking at my x-axis here. 1, 2, and then let's see. I've doubled my concentration on my substrate to 4. And what happened to my rate becomes 5. Then I've doubled my concentration of my substrate to 8. And I get this. I'm going to go ahead and double my concentration of my substrate to 16 nanomolar. And could somebody make an estimation or give me a number as to what roughly, based on these numbers and the trend that we're seeing in that graph, what do you think the velocity is or the rate of product formation is? I like it 5. Okay, so we're going 16 nanomolar, 5. Okay. Um, if we are to imagine that we continue going on, let's say extrapolating for 10 more trials. I always like to use the word extrapolating, but we got 10 more trials continuing to increase our substrate concentration. For one, that's not a crazy idea because enzymes do some bonkers things. Bonkers is a technical term, but in this case, we want to make sure that it doesn't. So we would continue and we would take the substrate concentration to such a height that we can confirm this is kind of a valid and reproducible graph of our curve. And it's nice to be able to say, okay, well, our curve it plateaus at a certain concentration. And the reason that it plateaus is we have given this enzyme as much substrate as it could possibly desire, as much substrate as it could possibly need. We bombarded that enzyme with substrate. Did our velocity change? Nope. It just kind of hit that plateau. Now, with that in mind, do you think that you could make an estimation as to the maximum velocity of this enzyme? Yeah, about 5. So the way that we're going to do that with a Michaelis-Menten curve is we look at our y-axis and we make an approximation. We say Vmax. We kind of draw a dashed line. We say roughly there. Now, is it exactly 5? Keep in mind, these are not real numbers, so it's roughly 5. Now, the other thing that we can do with a Michaelis-Menten curve is we can make a approximation of our enzymes affinity for our substrate. Now, if you're prepping for the MCAT or something, you're already familiar with these terms, um, fantastic. I hope that I only reinforce what you already understand. With this graph, we can make that approximation. And the way that we do that is we kind of take this calculation that we've put together, this y-axis with our Vmax, and we basically cut it in half. And we draw a line. We say, okay, well, our Vmax, is approximately 5. Therefore, half of our Vmax is about 2.5. And what we can do is say, well, how much, or ask the question, how much substrate, what concentration of substrate will get our enzyme to half of its maximum velocity? And we kind of draw a little, well, yeah, we're good. Okay, yeah. We make an approximation on our y-axis, then we coordinate with where our line is along our x-axis. So based on this, if this 2.5 is Vmax over 2, we can make an approximation or a rough calculation about our enzyme's affinity for the substrate. Now, whenever you think about binding affinity, if you think back to any other classes where you talk about binding affinity, does anyone remember the units that you used to measure the affinity? Typically, your units were going to be, great question, Madison. I'm going to get to that in just a second. It basically gets you to the units that we're going to use are going to be a concentration measurement. Now, Madison, why is Vmax over 2? Well, that is kind of the standard that we use to ask the question, how many of this enzyme's binding sites are occupied? So how much of this substrate is required to get half of all the binding sites occupied? Does that answer your question? Or, sorry, does my answer help answer your question or understanding?
Okay, let me just make sure. So I have it written down that the Vmax over 2 tells us how many enzyme what are binded? The enzyme sites?
So how many of our enzymes' binding sites or active sites are occupied by the substrate?
Okay.
So what we're looking for there is not necessarily like we got 2.5. That's half of our maximum velocity. But what we're most interested in is what concentration of our substrate gets us there. So you can kind of think about it as, well, if we give our enzyme, let's pick an extreme. If we give our enzyme 32 nanomolar of our substrate, our enzyme is going to work as hard as it possibly can. But that's going to put us approximately right here. The maximum velocity is going to be achieved. Done. Why would you give your enzyme 32 nanomolar if you could effectively get the same thing with 16 nanomolar? Or would you give your enzyme 32 nanomolar if only 16 would get you the same kind of velocity, the same rate of your product generation? No. Okay. Then you take it back a step and you say, all right, well, 16 got us to our maximum velocity. So too did 8. Why would I give it 16 if I can get away with giving 8? And you keep going back and back. until we reach this point where it's like half of our binding sites are going to be occupied and we're going to be able to produce this product if we give our enzyme, what would that be? Approximately 1.5 nanomolar of our substrate. Okay, so with this graph that I've just drawn here, we have two of our kinetic parameters that are super important. One of those kinetic parameters is known as our Vmax. In this situation, our Vmax is 5. Does that number have units? It absolutely does. Those units are 5 nanomolar per minute. 5 nanomolar of our product are generated every minute. Our next kinetic parameter, well, is known as a Km. It's a measure of our enzyme's affinity for our substrate. Our Km, add to the chat what our Km is. And I'll give you a little bit of a hint. It is a concentration, but what is that specific value that I'm looking for? 1.5 nanomolar. Now, if you'll give me just a minute, I'll give you kind of a analogy that I always like to think about with respect to this. When I was in high school, I worked at the Old Country Buffet and I washed dishes. And I remember they interviewed me and they were like, Joel, we're going to give you $5.50. And at the time, minimum wage was $5.15. And I thought to myself, oh my gosh, I'm just pulling the wool over their eyes. 35 extra cents an hour. They have no idea. I didn't even negotiate. Always negotiate your salary. Always. Now, with that said, I did not negotiate. But had they come back to me and they said, Joel, you know what? We're gonna bypass labor laws and we're gonna give you $12 million an hour to wash dishes, I would have gladly accepted that money. If they would have instead, or in an alternate dimension, said, Joel, guess what? We're gonna give you 15 cents an hour to wash dishes. Chances are I was I was dumb, so I probably have been like, oh, okay. But that would not have been a good decision. So if they gave me that much and they were like, you have to do this job, you're getting paid 15 cents an hour to wash dishes, I would have been like, well, okay, here's what I'm going to do. I'm not going to work as hard as I possibly can. If they had, by contrast, given me $12 million an hour to wash dishes, I would have been like, you are never going to see someone wash dishes faster than me or better than me. So I would have reached my maximum velocity if they gave me $12 million an hour. That's this data point right out here. If they would have then been like, okay, we'll give you $6 million an hour. You know what? I'm still going to wash dishes really damn fast. Sorry for swearing. $1 million an hour. They would continue to creep that number down. At some point, if they're like, we're going to give you $13 an hour, I think I might wash dishes slightly slower than if they were going to give me $20 an hour. And that's where this number comes in. My affinity, am I passionate about washing dishes at a buffet restaurant, or was I whenever I was 16? No, I was not. So my love for the game was very low, but they gave me the financial incentive. And so I'd be like, okay, I'm going to work hard for this. Our affinity, our enzyme's affinity, our Km is kind of that sweet spot, that Goldilocks spot where it's like, okay, we're going to give you this much of the substrate. We're not asking you to go as fast as you possibly can, but we want a measurement, a comparable measurement that we can look at all other enzymes. Now, why is it 50? Why is it half of Vmax? That's going to come back whenever we look at a couple of other kinetic parameters. Now, thank you for letting me steal about 3 minutes of your time to share my labor experience in high school. I left that job and I didn't show up for my last day. Ha! Because the other person who did the same job before me also did not show up for their last day, so I thought that was like tradition. Um, anyway, here we go. So this is kind of in a nutshell, another way of looking at it. We have our substrate concentration, that's measured in molarity. Initial velocity, or our rate, is measured as a concentration of our product over time. On the far left-hand side of our curve, well, our enzyme's probably not going to be doing too much, but then on the far right-hand side of our curve, our enzyme's going to be doing a lot. Now, a nice additional visual of this is shown here. And this is a little bit more realistic because one of the things that's worth noting is if you look at the line, the dashed line at probably like 0.335 or something like that, where our Vmax is. And then if you look at our data line, one of the things that I really think is important to stress is that this dot right here represents a trial number 6 or something, trial number 7. So all of these, this is just the trend line. I stress that because one of the things that I've noticed is that people like to draw this line and then they kind of lose the forest for the trees, recognizing that that's a trend line. So keep that in mind. Okay, I just got a private message that was, how do we get 1.5 from Vmax over 2? Well, the way that we got 1.5 from Vmax over 2 is because our y-axis shows us our velocity. So we take our Vmax and we divide it by 2. We basically cut that in half. Our Vmax was 5. Then we ended up at Vmax over 2, or 2.5. We then draw a line that coordinates our x and our y-axis. Our y-axis coordinate is 2.5. Our x-axis coordinate is this 1.5, which shows us our substrate concentration. I hope that answered your question. Okay, so now where we go from here, when you look at this data set, when you look at this curve right here, it's not linear. That's not really a secret to anyone. If it was linear, then we could double our concentration and our velocity would increase by that factor. It would double. This is not linear. Working with non-linear data is a little bit less fun than working with linear data. Now, here's just another depiction of that Vmax and Km. What we want to be able to do is take this graph, this Michaelis-Menten curve, and convert it to a linear data set. Now, with this, back to that just a second. Okay. In order to do that, what we will do is we will take all of the values that make up our y-axis and we'll calculate the reciprocal of them. Then we'll take up all the data that matches our x-axis and we'll calculate the reciprocal value of that. And we will make what's known as a Lineweaver-Burk plot, or what's commonly known as a double reciprocal plot. This is effectively the exact same thing, except the reciprocal. Now, with that in mind, one of the questions that I'm always asked, or that I'm regularly asked is, well, how do I do that? And here's where it goes back to what's important about our data set. We have all of these values, T1, T2, T3, T4, and so on. How could I get the reciprocal of velocity where it is 2? Let's say this data right here. You can add it to the chat if you'd like. 1 over 2, done. But what about 1 over 1? Oh, same thing. Oh, 1 over 1, oopsies. Trying to be snarky and then I do something wrong. How do we calculate the reciprocal of 4? 1 over 4. 1 over 5. This is all that we do. The initial velocity data, or the reciprocal of this initial velocity data, is going to be plotted for our y-axis. And then when you do the same thing for your substrate concentration, and you calculate the reciprocal of your substrate concentration, that's going to be your x-axis. I think that there's a tendency for people to take this plot, this Michaelis-Menten plot, and convert it to, and think about the conversion to a Lineweaver-Burk plot and think, well, it's got to be really complicated. It doesn't. and it's not. The y-axis, which is, if you remember the y-axis of a Lineweaver-Burke plot being 1 over initial velocity and the x-axis being 1 over substrate concentration, well, then you're in a good position to know that your Michaelis-Menten plot is y-axis initial velocity, or v sub 0, and x-axis is substrate concentration. Now, just as a little bit of a reminder, um, where is enzyme concentration measured? Is it? Is that plotted here? Not at all. The enzyme concentration for all of these, or for both of these plots that we've looked at, it's fixed. You don't have to think or worry about it. So a very good and fair question then is, why would I need a Lineweaver-Burke plot whenever I have a Michaelis-Menten plot? Well, one of the reasons is that you get kind of a more accurate approximation of your variables. Because if you remember when we looked at the Michaelis-Menten plot, we said, oh, that looks roughly where our maximum velocity is. And we drew our dashed line there. And from that dashed line, we calculated our half of Vmax. And then we calculated our Km based on that. Well, when you take this data and you get this double reciprocal data and you plot it out, well, then you get a nice plot that looks like this, a nice straight line. And with that straight line, you have a couple of important variables. You can figure out your Vmax because your y-intercept, your y-int, is equal to 1 over Vmax. Now, what I think is helpful in this moment is to think about what are the coordinates. If you think about not necessarily battleship, but plotting something, you've got your x, y coordinates. We want to know what our y-intercept is. And this right here would match for the y equals mx plus b. If I wanted to solve for y, what would I do? Imagining that I have my m and my b, I would plug in a 0 for, would I plug it in for y? No, I plug it in for x, because my y-intercept is going to be x coordinate of 0, which is right here, and then whatever right here. Does that make sense? So that's like the value of a Lineweaver-Burke double reciprocal plot is that we get our data to match this equation right here, which I think the first time I saw y equals mx plus b was in 4th grade in Mrs. Rennick's class. Now, whenever you use that and you solve for y, you get your y-intercept. One of the things, let's say hypothetically, that somebody gets a y-intercept of 17. That is my y-intercept. What people have a tendency to make a quick mistake on is they say, well, there we go. My Vmax is 17. Yes, we would say 17 is equal to 1 over Vmax. So we'd do the algebra and we'd say Vmax is equal to 1 over 17. Okay, I just got a private message. Why do we plug in 0? Sorry, it didn't make sense. The reason that we're plugging 0 in is because if you get this equation, if you plot all your data and you get this line, or you get this trend line, that's going to be y equals mx plus b. That's the equation for a line. What we need to figure out is what is the value of y when the value of x is 0. So we would have something like y equals, you get this in Excel, it'd be y equals 1.2x plus 0.94. Okay, so this line right here, this blue line, is explained with this y equals mx plus b formula. What we're going to do is we need to figure out, well, where does that line cross our y-axis? Well, that line crosses our y-axis when x is equal to 0. Because if you look down here, 1, 2, 3, -1, and so on, that line is crossing that y-axis whenever our x is equal to 0. Okay, I'm happy. Thank you. I've had a couple of instances in the past few days where somebody asks me a question, then I give an explanation, and then they don't respond. And so I'm like, was that like a great explanation, Joel? Or did that make things worse? And when I don't get a response, I'm worried that I just made it worse. Um, okay, so that's what we have to do there to solve for our y-axis, or to solve for our y-intercept, and therefore solve for our Vmax, because our y-intercept is equal to 1 over Vmax. Now, next up, the value of a Lineweaver-Burk double reciprocal plot for Km. Well, our Km is very similar. So let's say hypothetically, no, I'll rewrite that. Y equals mx plus b. If I give you the equation for a line, and I say it's 1, or y equals 1.2x plus 0.94. And I said, what is your Km? What you would want to do in that instance is you would say, okay, I'm describing this blue line. And I know that whenever I plug 0 in for x, I get that. Okay. What I need, however, is I need to figure out where this line, where my blue line crosses my x-axis. And if I look at my y-axis, I got 1, 2, 3, and so on. That y-axis goes down, so that's -1, -2, and so on. This blue line will cross my x-axis when y equals what? When y equals 0. So then what I'm going to do is I'm going to take my equation, and I'm going to say 0 equals 1.2x plus 0.94, and I'm going to solve for x. Now, whenever I do that, one thing that I notice right off the bat is I'm going to get negative 0.94 divided by 1.2 equals x. I skipped a couple of steps on rearranging the equation and doing the algebra there. What is going to be, not the magnitude, but is my value for x going to be positive or negative? It's going to be negative. Now, with that in mind, if I told you that this, ignore this, just look at my number line. If I said that this was -5 on my x-axis, would you believe me? Okay, great. So that's -5. Um, my x-intercept here is equal to -1 over Km. Is that negative value significant? Absolutely. Because what I can then do is, let's just go, if we went back to our equation, and just for the sake of kind of reducing confusion and jumping all over the place, I'm going to say calculator, say 0.94 divided by 1.2. Now you get 0.783. That's my x-intercept. I'm going to set that equal to negative 1 over Km. The value that I solve for my Km, is it going to be positive or negative? It's going to be positive. You're right. I'm going to solve for that just by doing the algebra. The negatives cancel out. 1 over 0.783 gives me my Km. Now, this is a nice little check. If you ever arrive at a problem where you solve for your Km and your Km is negative 0.5, we'll say, what are the units for Km? Or does Km have units at all? Spoiler, it's got units. They're going to be a concentration, like a molar concentration. Would it make sense to have a negative 0.5, let's say nanomolar concentration? The way that I like to think about that sort of thing is say, has anyone ever said, hey, next time you go into lab, make a negative 0.7 molar sodium chloride solution? No. If they did, your response would be, interesting. Very curious. Does that make sense? Can I get a thumbs up or a yes that, okay, cool, I got it? Okay. Wonderful. Okay, so what we've got is our Michaelis-Menten curve. That shows our enzyme data in a non-linear fashion. We have our Lineweaver-Burk plot, also known as our double reciprocal plot, which takes non-linear data and linearizes it. If there are two things that I think are most invaluable or extremely helpful to remember, they are that your Lineweaver-Burk plot, your y-intercept is 1 over Vmax. Your x-intercept is negative 1 over Km. And in the event that you're ever like, ooh, that doesn't make sense, just remember, your x-intercept is going to be a negative value because a concentration has to be a positive value. Now, with that in mind, I will ask questions about what are the labels of the x and y axes of Lineweaver-Burk and Michaelis-Menten plots. I will ask you, based on this graph, calculate the Km, calculate the Vmax. I would, yeah. I feel comfortable answering that with a yes. So that double reciprocal plot is the one that we're going to see a little bit more of. We're going to see more of it because when we look at and analyze enzyme inhibition, that curve, that blue line, is going to move based on a type of inhibitor. So our Vmaxes are going to be very similar to one another if you're looking at a Michaelis-Menten or a Lineweaver-Burk plot. Now, if I can make a recommendation with respect to these plots, I would try to treat them as, okay, this is a fundamental, I get it, I'm moving on. And spend more time thinking about inhibition than saying, oh, I have to completely understand every aspect of these two plots before I can even begin thinking about inhibition. Just because I've seen from my own personal experience, I did that and then I just fell behind on everything. And I'm not saying that to like intimidate you or anything like that, but I always kind of think about these plots as being similar to, okay, you're learning how to play basketball. First, you got to dribble. Okay, cool. Are you going to spend 5,000 years learning how to dribble? No. You're going to then be like, okay, now I'm going to run and dribble at the same time. Okay, so now we're talking about inhibition. There are two major types of inhibitors. An enzyme is a protein for our purposes, that's going to take a substrate or substrates and produce a product. An enzyme inhibitor is a molecule that an enzyme will bind to and not be able to then pick up its substrate and catalyze its reaction. That's one potential mechanism and way that it works. There are two major types of inhibitors. One is an irreversible enzyme inhibitor. These are known as inactivators. These bind permanently to an enzyme. So if you think about the types of interactions that a inactivator would have, it's more than likely going to have some covalent bonding. Now, these are reagents that chemically modify an amino acid typically. So what they will do is they'll say, okay, well, here's the protein, here's the enzyme that does anything. I see these are the amino acids that are involved in the active site and binding to the substrate. Let's just bust those up. That's what they will do. Alternatively, if you think about an enzyme, here's our enzyme. An irreversible enzyme would be like a pair of scissors. It'll roll along, find that, and I'm going to see if I can redraw this. Basically, clip that enzyme up into a couple of pieces. So those molecular scissors would be an example of an enzyme inhibitor. Cuts it up, that enzyme can't come back to work. A reversible enzyme inhibitor. And this is where we're going to focus most of our attention. And this is where we have multiple different types. These typically target the binding site. And the inhibitor is not reactive. So I always kind of think about between the two of them, if you are a cyclist, every so often you'll get scared that you're going to ride over a stick and that stick will break and pop up and land in your spokes. And then all of a sudden it busts up some of your spokes on your wheel. And if I say that because that has happened to me and it just busted up a bunch of my spokes. That stunk. Think about this as, well, an inhibitor that is reversible is the stick that pops into your fork and pops into your spokes and just kind of jams it up. What can you do with that inhibitor? You can remove it. An alternative, an irreversible inhibitor, would be somebody with pliers that comes along and cuts all of your bike spokes. What are you going to do? You got to get a new set of spokes, retool the wheel altogether. Now, these reversible inhibitors typically compete for the binding site. These are also often known as, they are often known to be what are known as transition state analogs. So what that means, and we'll get into this a little bit more next week, is they resemble basically the substrates as they are becoming products. So they kind of look like something similar to that. In which case the enzyme's like, okay, cool, that looks like what I need to bind to, and it will bind it, and then it'll be like, oh crap, I can't do anything with this. Now, reversible enzyme inhibition. There are four major types. There are competitive, non-competitive, mixed, and uncompetitive. These different inhibitors impact enzymes in a different fashion from one another. The first of which is a competitive inhibitor. Now, what a competitive inhibitor is going to do is it's going to compete with the natural substrate for the enzyme. We will talk about all of the different permutations that exist, and we'll also talk about a Ki. That's kind of like a Km, but it's an affinity that an enzyme has for an inhibitor. Basically, how effective is an inhibitor? Another thing that I want to make clear, or I want to emphasize before we proceed, is that two of these words on here they're very tempting to use interchangeably. Would anyone care to add those words to the chat? I'll add one, non-competitive. What is the other word that you might want to be like, oh, well, that's the same thing? Uncompetitive. You're absolutely right. Don't fall for the trap thinking that non-competitive and uncompetitive are the same thing, because they are not. And they have different impacts on an enzyme. So what we've got here are a Michaelis-Menten plot and a Lineweaver-Burke plot that shows how a competitive inhibitor works. What we're going to do today, and what I'm aiming to do today, is at least get through competitive inhibition, and then maybe we'll get through non-competitive as well. But what I want to do more than anything is get through competitive inhibition. If you look in the lower left-hand corner, we've got that Cleland notation where we're talking about our free enzyme. And the way that I like to imagine this is that we've got a beaker right here. And in that beaker, we've got our free enzyme, we've got our substrate, and we've got our inhibitor. And for that, we've got the opportunity. Our enzyme basically has a chance to bind to the substrate. Our enzyme also has the chance to bind to the inhibitor. Now, if this inhibitor is a competitive inhibitor, well then, that enzyme, that free enzyme, can bind to it and form what is known as the EI complex. If anyone is or at least at one point was a fan of pop superstar Nelly, when I was in high school, he was very popular 25 years ago. A little bit less popular now. At any rate, Nelly had this song where he'd say, EI, EI, uh-oh. That song was about competitive inhibition. You have to listen really closely to the lyrics, but it was, in my mind. Now, with that to say, is it exactly a coin flip for what the enzyme's going to bind to? Is it just like, oh, I'll either bind to the substrate or the inhibitor? Not really. And a fair question for that is, why? Well, enzymes will have different affinities for different molecules. If an enzyme has a very, very high affinity for one substrate and a relatively low affinity for the inhibitor, it's not going to bind to it. But essentially, on a molecular level, this enzyme has a binding site, and the substrate and the inhibitor both see that binding site and think, that's a couch made for me. I'm perfect for that. So, what do you think about the structure of a substrate versus the structure for a competitive inhibitor? How do you think that you describe them? Add to the chat what your thoughts would be, or presumption. Similar. You're absolutely right. A competitive inhibitor and a competitive inhibitor is probably going to have some functional groups or multiple functional groups that are kind of spatially set to look like the natural substrate, so that the enzyme will be like binding, done. Okay, now let's look over at our Lineweaver-Burke plot. Our Lineweaver-Burke plot right here, where I've just drawn my green star. It's kind of an olive-colored line. That's our double reciprocal plot where we have no inhibitor present. And when no inhibitor is present, we see our line. Okay, and again, this is a double reciprocal plot. All of these, this trend represents all of these trials. Then over here, we've got this line. This second line denoted as, it's kind of a navy with an alpha equals 2. In all of those trials, and this is an important thing to remember, we keep the we keep the inhibitor concentration constant. For all of the trials, you will maintain the same inhibitor concentration. So the only thing that you're changing is your substrate concentration. Now, what do you notice about that slope of that line, of the A equals 2 line versus the A equals 1 line? Add to the chat what you think. Steeper. It increases. Okay. Then if we go one more to our A equals 4, it's kind of a purple line. Well, the slope increases even more. So in this series of trials, what we see is that as you continue to increase the inhibitor concentration, going from this trial where I put my X to this one where I put a Red Hot Chili Peppers logo, what I see is that my slope increases. Now, what do you notice about the kinetic parameters that are important to us on that double reciprocal plot? Add it to the chat what you see. Our Vmax is constant. You're absolutely right. And it says, Vmax stays the same. I think that it's important to look at them. Madison, you're absolutely right. Okay, Madison pointed something else out. Our Km changes. Now, one of the things that's important to remember is that this is a reciprocal value. So with a competitive inhibitor, Vmax unchanged. Km. What happens to our Km? Okay, well, one thing that we can do is we can look at, it's helpful for me to do this just because my brain sometimes works better than other times. In this moment, what I'm going to do is I'm going to look at my Michaelis-Menten plot. I've got the exact same data, but it's not plotted as a reciprocal value. Instead, I'm looking at my Michaelis-Menten plot. What I notice is that, well, the curves sort of shift to the right. If I think about my x-axis here, if I'm going to go ahead and call this 1, 2, 3, 4, 5. Whenever I've gone from no inhibitor to including the inhibitor, then I am increasing my inhibitor concentration. What is happening to my Km? It is also increasing. So my Km goes up, which is why when we look at our double reciprocal value, well, we get closer and closer to 0. Now, okay, so what we have taking place here is we have our free enzyme. It can bind to either the inhibitor or the substrate. If it binds to the inhibitor, Nelly is pretty pumped about that. uh-oh. If it does not, then the free enzyme binds to the substrate, and we get this ES complex. If that ES complex is formed, are we going to make our product? We will. We will proceed. As soon as ES is made, we're going to make our product. We're going to make that product P, and we're going to release our free enzyme. So that free enzyme can run back here. Now, one thing that I'd like you to know about Km and the magnitude of Km. As a general rule, or as a good rule to follow, a low Km means high affinity. A high Km equals low affinity. And then I'm just going to add this for substrate. Okay. Now, with a competitive inhibitor, our Km goes up. What does a Km increasing say about our enzyme's affinity for our substrate? Our Km goes up, and a high Km means a lower affinity. That means, yes, our affinity for our substrate goes down than in the absence of that inhibitor, or compared to the absence of the inhibitor. So a competitive inhibitor basically blocks or competes with a substrate for the binding site or for an enzyme's binding site. No, our affinity, let me, competitive inhibitor causes enzymes affinity for substrate to decrease. Is there inhibitor affinity? That's a great question. And we're going to tackle that next week. That's what Ki stands for. So I'm, ugh, these are great questions. Those are fantastic questions because to me, the heart of those questions are you're recognizing a couple of things. One enzyme can have two different inhibitors. Second, of those 50 different inhibitors, one might arguably be a better inhibitor than another. So if an enzyme, like if you imagine that you had an inhibitor that was fantastic, it would knock out the activity of an enzyme, but the enzyme didn't really want to bind to it. Is it going to actually work? And if you think about this, or when you're thinking about this, try to apply it to the context of drug design. Like there might be a drug that is fantastic, but you have to have a 7 molar concentration of it in your bloodstream. How likely are you going to be able to have 7 molar anything in your bloodstream? Pretty slim. In which case, then it's like, well, it kills the disease and the host. Not a good drug. Okay, I feel comfortable stopping here. We are going to pick up with this stuff on Monday. Thank you so much for coming to class, everyone. Um, we did not have any poll questions today, but I got the attendance, so we're good there. I'm stopping my share. I hope you guys have a great weekend. If you have any questions, let me know. I can meet with you on Zoom tomorrow or Friday. But just let me know. I hope you guys have a great weekend. And let me know if there's anything I can help you with.